The NEC text does not explicitly address cooling tower fan motors, so it is up to the authority having jurisdiction to interpret the code and make a determination. However, based on the explanation, it appears that the fan motor is being used for continuous duty as it operates continuously with load under most conditions of use. Therefore, it would not fall under the classification of varying duty service as defined in Table 430.22e. Regarding the wiring and protection from the variable speed drive output to the motor, there is no specific code requirement for 200% full load amps rating. However, it is good practice to follow the manufacturer's recommendations for wiring and protection. Some variable speed drives may generate voltage spikes or harmonics that can damage the motor or wiring if not properly protected. The term standing wave is not specifically used in the NEC in relation to variable speed drives. It is a general term that refers to a wave that does not dissipate and remains stationary. In the context of electrical systems, it can refer to a voltage or current wave that reflects back and forth between 2 points, causing high voltage or current levels. It is possible that the standing wave phenomenon could occur in the wiring between the variable speed drive output and the motor. This could be caused by impedance mismatching between the variable speed drive and the motor. However, it is not a common occurrence and is unlikely to cause damage if the wiring is properly designed and installed. It appears that the customer's interpretation of the NEC regarding the classification of the fan motor and the wiring requirements for the variable speed drive output is incorrect. It is always advisable to consult with a qualified electrician or engineer to ensure compliance with the code and proper operation of the equipment. Now let's delve a little deeper into these topics. Firstly, considering the motor classification, Table 430.22e in the NEC addresses conductors supplying motors used for short time, intermittent, periodic, or varying duty. The fundamental question here is whether the cooling tower fan motor truly falls under one of these categories. Continuous duty, as the name implies, signifies operation at a substantially constant load for an indefinitely long time. In contrast, varying duty involves operation at varying loads for varying durations. The note you mentioned in the NEC is crucial. Any motor application shall be considered as continuous duty unless the nature of the apparatus it drives is such that the motor will not operate continuously with load under any condition of use. This places the burden of proof on demonstrating that the motor will not operate continuously under load. In the case of a cooling tower fan, the primary purpose of a variable speed drive is often to maintain a consistent temperature by modulating the fan speed. This implies continuous operation, even if the speed varies. The absence of frequent starts and stops further supports the argument for continuous duty classification. Now let's examine the wiring and protection aspects from the variable speed drive output to the motor. While a blanket requirement for 200% full load amps rating may not exist in the NEC, several factors necessitate careful consideration of conductor sizing and protection. Firstly, harmonic currents generated by variable speed drives can significantly increase the current flowing through the conductors. These harmonics are multiples of the fundamental frequency and can lead to overheating and premature failure of the wiring if not properly accounted for. Secondly, voltage spikes, or overvoltages, are another concern associated with variable speed drives. These spikes can stress the insulation of the motor and wiring, potentially leading to insulation breakdown and short circuits. Thirdly, the impedance matching between the variable speed drive, the motor, and the connecting cables plays a critical role in minimizing voltage reflections and standing waves. An impedance mismatch can cause voltage reflections to travel back and forth along the cable, resulting in voltage doubling or tripling at certain points. These voltage surges can damage both the motor and the variable speed drive. In addition to these factors, the NEC provides specific guidance on conductor sizing and protection for motor circuits. Section 430.22 generally requires conductors supplying a single motor used in a continuous duty application to have an ampacity not less than 125% of the motor's full load current rating. This additional capacity is intended to account for the motor service factor and potential overload conditions. Furthermore, Section 430.52 addresses motor branch circuit, short circuit, and ground fault protection. The type of protection device, such as a circuit breaker or fuses, and its rating or setting, depend on the motor's characteristics and the application. In cases where harmonic currents are present, it may be necessary to use specially designed circuit breakers or fuses that are rated to handle the non-sinusoidal waveforms. Now, let's discuss the term standing wave in more detail. While not explicitly mentioned in the NEC in the context of variable speed drives, the concept is relevant to understanding potential voltage and current phenomena in motor circuits. A standing wave occurs when two waves of the same frequency travel in opposite directions and interfere with each other. In electrical systems, this can happen when a voltage or current wave is reflected back from the motor terminals due to an impedance mismatch. The reflected wave combines with the incident wave, creating a standing wave pattern with areas of high voltage or current and areas of low voltage or current. The amplitude of the standing wave depends on the degree of impedance mismatch and the length of the cable. In severe cases, the voltage at certain points along the cable can be significantly higher than the source voltage, potentially exceeding the insulation rating of the wiring and motor. To mitigate the risk of standing waves, several measures can be taken. Firstly, using shielded cables can help to reduce reflections and attenuate high-frequency components. Secondly, installing a line reactor or a filter at the variable speed drive output can improve impedance matching and reduce harmonic distortion. Thirdly, selecting a motor and a variable speed drive that are designed to work together can minimize impedance mismatches. Furthermore, following the manufacturer's recommendations for cable length and termination is crucial. Now, let's consider the practical implications of these concepts for a cooling tower fan motor application. Given that the primary objective is to maintain continuous operation at varying speeds, it is reasonable to classify the motor as continuous duty. This means that the conductors supplying the motor should be sized according to Section 430.22 of the NEC, typically at 125% of the motor's full load current rating. Additionally, the motor branch circuit, short circuit, and ground fault protection should be selected based on Section 430.52, taking into account the motor's characteristics and the presence of harmonic currents. While 200% full load amps rating for the wiring may not be strictly required by the NEC, it is essential to ensure that the conductors are adequately sized to handle the harmonic currents generated by the variable speed drive. This may involve directing the conductors based on the harmonic content of the current. Furthermore, it is crucial to follow the manufacturer's recommendations for wiring and protection, as they may have specific requirements based on the design of their equipment. In conclusion, while the NEC does not explicitly address every aspect of cooling tower fan motor applications with variable speed drives, it provides a framework for ensuring safe and reliable operation. It is important to carefully consider the motor's duty cycle, the presence of harmonic currents, and the potential for voltage spikes and standing waves. Consulting with a qualified electrician or engineer is always advisable to ensure compliance with the code and proper application of the equipment. They can assess the specific requirements of the installation and recommend appropriate wiring, protection, and mitigation measures. This comprehensive approach will help to prevent premature failure of the motor, wiring, and variable speed drive, and ensure the long-term reliability of the cooling tower system. Finally, remember that the AHJ has the final say in interpreting the code and making a determination. It is always best to consult with them to ensure that the installation meets their requirements. They can provide valuable guidance and clarification on any ambiguous code provisions. This collaborative approach will help to ensure that the installation is safe, compliant, and meets the needs of the application.